Alright, so one question that came up on coding instructions, we'll talk more about other coding anomalies, but let's talk about this goto statement. This is in chapter 2 of the text. Goto is one of the few instructions that actually takes 32 bits instead of 16. Remember when we looked at our instructions, we had this basic format. We had 6 bits for opcode, we had a destination, we had an access bit, that's 8, and then 8 bits for a file register, 16 bits, 1 instruction. There's a few instructions that actually take 2 of these words, so they're 32 bits, and goto is one of those. Goto is an instruction that says, instead of executing the next instruction in memory, I want you to switch and start executing some location somewhere else. Okay, it's a jump. So it changes the instruction flow. Normally it just executes instruction 0, 2, 4, 6, 8, 10, 12, and it just keeps going like that. If you get to a goto and you say go to 500, the next instruction it executes will be instruction 500. So it breaks the program flow. And it's coded as 2 16-bit words. The first one begins with 1110, 1111, and the second one begins with 1111. And that leaves us 4, 8, 12, 16, 20 bits that we have to specify. And these 12 bits basically get chunked on to the left of these 8 bits. So this is labeled K19 through K8, this is K7 through K0. So think of these 8 bits followed by these 12 bits, you've got a 20-bit number. And that 20-bit number tells it what instruction is branching to, with one little detail. Remember I mentioned that all of our instructions are stored at even locations. First instruction is 0, and then 2, and then 4, and then 6. So when we write out the address of the instruction we want to branch to, we don't need to specify the least significant bit, because we know that's always a 0, it's always an even location. So when you code an instruction like this, and this is K19, K8, K7, K0, the instruction that you're actually branching to is the one stored at K19, K18, K8, K7, K1, K0, and then an extra 0 on the end. So we're specifying 20 bits, but it's actually a 21-bit address that we're branching to. And that's all summarized in this succinct little notation. K is loaded into PC 20:1. PC, the program counter, that's the address of the instruction you're about to execute. And these 20 bits of K get loaded into 20 bits of the PC, but not starting at position 0, starting at position 1. So it loads into this part of the program counter. So the example is, here's a goto instruction, figure out what address we're branching to. So this is K19 down to K8, and this is K7 down to K0. So the address we're branching to is that with an extra 0 on the end. So if you want to write that in hexadecimal, you break it up into groups of 4, and that gives you 0, 1, 0, 5, 0, 2, x, which is what your new program counter will be after the goto. So that's what's going on with that, and there's a few other instructions that do the same thing. Does that make sense? So these 12 bits followed by these 8 bits followed by a 0, that's the address you go to. table 20-1. Our table of instructions. So how can we interact with individual bits to do input and output to particular pins when everything is byte oriented? When every time we say load this value in this register, it always loads 8 bits. Whether we wanted to deal with all 8 bits or just 1 bit. So an easy way to deal with this is with a set of bit instructions. So there's 5 instructions in particular that will be useful for us here. This first one is bit clear, and it lets us set a particular bit in a register to 0. So for example, I could say bit clear file register, and your arguments are first the file register, so I don't know, 0x80. I'm assuming I care about file register 80 for some reason. Followed by the number of the bit that you want to force to a 0. You've got 8 bits, bit 0 through bit 7. So I don't know, let's pick on bit 3. And I'm going to ignore the access bit again, because the compiler, the assembler will set that up for us. So bit clear f 0x80, 3. Here's what this is going to do. Inside my general purpose memory, there's a file register stored at location 80. These are bit positions 0 through 7. This instruction will write a 0 into this bit, and it won't touch the other bits. So if I wanted to do output on RA3, so let's do this. Do output on RA3. Output, I gotta write a 0 into bit position 3 on tri-state A. So I can do that in one instruction, bit clear file register tri-state A, 3. And it will basically look at the current value in tri-state A, and it'll change whatever the value of bit 3 is to a 0, and it'll leave the other bits unchanged. If I want to do input on RA2, I can do a bit set file register. Tri-state A is the register I want to manipulate, and bit 2 is the bit I want to set. And this will force a 1 into bit position 2 on tri-state A. And now RA2 is set up for input. So you can set individual bits, and you can clear individual bits using bit set and bit clear. And there's also a bit toggle. So if you just want to flip the value of one particular bit, you can say bit toggle file register, bit number. Of course, you could read the value and see if it's a 0 or 1 and then do a set or a clear accordingly, but bit toggle takes care of that for you. And if you want to code these instructions, this is the coding of them. So the opcode in these cases is only 4 bits. And the next 3 bits code the number of the bit that you want to manipulate. So for example, if I want to do bit clear file register 80, 3, how would I code that? 1001. The bit number I'm asking to manipulate is bit 3, and I have to write that as this 3-bit number BBB, so that's 011. The access bit I'm going to ignore. And then the file register itself was 80, which looks like that. So let's just pretend the access bit is 0. So the coding for that bit clear file register 80, 3 instruction would be 5680 x. Sorry, 96. So code's just like the other instructions, except we have this special field, BBB, that's the 3 bits of coding to tell which bit we're working with. And there's no destination bit involved. This is always manipulating a bit in a file register. So we can clear, we can set, we can toggle. All right, these next 2 instructions are really cool, and they show something that we can use in a lot of different cases, not just dealing with bits. They're called skip instructions. Okay, here's what a skip instruction does. Normally, we execute one instruction in the program memory, and then we execute the next instruction, and then we execute the next, and we just keep going. Execute this instruction, and then this, and so on. And if we have a go-to, then we go somewhere else, but forget about go-tos for now. We just execute instructions sequentially. In some cases, we can have an instruction which says, skip the next instruction. If this says skip the next instruction, here's what happens. We execute this, we execute this, we execute this, we skip this, we don't execute it, we go on and we execute this, and we keep going. So a skip is a way to say, I want you to keep executing sequential instructions except for the next one. I want you to skip over that. And it still takes a clock cycle, but the effect is it changes that instructions to do nothing. It's a no-op. So if that said clear some file register, it doesn't get cleared. Okay, why do we have skips? Because they give us an easy way to do conditionals. So these 2 instructions say bit test a file register and skip if that bit is clear or if that bit is set. So we can pick a file register, including a special function register. We can pick a single bit within that register. We can say test that bit, and then conditionally skip the next instruction depending on whether that bit is a 1 or a 0. And this is a really powerful way to do if-thens. Now we only get to skip one instruction, but that instruction could be a go-to that takes us somewhere else. And by skipping that, we can go on to the following instruction. By not skipping it, we can branch somewhere totally different. And there's skips based on bits, there's skips based on whether something's equal to 0, there's skips based on whether something is positive or negative, there's a whole bunch of different skip instructions. But this is the one that's going to be most useful for now for doing I/O, because here's what we can do. Let's say read pin 17, and if it's equal to a 1, let's increment file register 80. And let's do this in a loop. All right, well, first thing you got to do is go back and figure out what pin 17 is. And pin 17 is RB2. So let's write a program to do this. So I'll put my org statement in the beginning to say start at location 0. That's where the processor starts when you apply power. And if we want to do input from pin 17 RB2, what things do we have to do again? port B, so we got to do something with tris B. So we need to set RB2 for input. So input, we want a 1 or a 0 in tris B. We want a 1, and we want it in bit position 2 because this is RB2, right? So we want to put a 1 in bit 2 of tris B, bit set file, tris B, comma, 2. And this says force bit 2 of tri-state B to B1. So now we're set for input. We need to put 7F or FF into ATCON1 to say this is digital instead of analog. And we'll subcontract that out for now. We'll get somebody else to write that for us. But we'll come back to it in a little bit. All right, now we want to look at pin 17, RB2. How do we read what the value of an RB input is? We look at port B, right? Port B is the collection of RB0, RB1, RB2, RB3, all of those 8 bits. And we want to know whether bit 2 is equal to 1 or a 0. So here's what we can do. So my comment here is read RB2 and skip if it's equal to, skip if it's clear, skip if it's equal to 0. So we're reading that pin 17, and if it's equal to 0, we're going to skip the next instruction. If it's equal to 1, we won't skip the next instruction. How do I increment file register 80? Remember? INCF. So skip if that pin is 0, otherwise increment that file register, which probably has some meaning better than 0x80. And now, regardless of whether we skipped or not, we're going to execute this next instruction, because skip only skips one instruction. And here I could do something like go to loop. And in my code, I can say something like loop, starting in column 1 with a colon at the end, that's called a label. And the assembler will figure out what the location in the program memory is for this point in my program, and when I say go to loop, it'll code it to say go to whatever this address is. And so this will loop forever, continually checking bit 2, pin 17, and anytime it's a 1, it'll increment location 80, and then it'll go back up to the top. If it reads pin 17 and it's a 0, it won't increment, but it'll still go back up here and test again. So there's a simple loop, and here's my end statement, and there's a program. Still with me? All right, we need a few more things to do this lab. So this will let us test individual bits. We can set and clear individual bits. So in your lab, you're going to actually read from port B. You're going to get 8 bits in, but you're going to interpret them as follows. These 2 bits will be the 2 bits of the first number you want to add. These 2 bits will be the 2 bits of the second number you want to add. this is what you read. And then you want to write your 3-bit sum into these 3 bits. So we've got a single port, port B. These 2 bits are one number, these 2 bits are one number, and these 3 bits is where we're writing our answer. So we're doing some reading and we're doing some writing on the same port.
Does it matter which specific bit you're using for those 3 sums? That you get 4 sums?
As in, could they be somewhere else?
Yeah.
Well, they can't be anywhere here because we're using these for inputs. So we could move them over one, but for the lab, you got to put them in those 3 upper positions.
Okay.
Well, adding 2 numbers in the PIC is pretty easy because it has an add instruction. It'll do 8-bit addition for us. We're only trying to do 2-bit addition. That should be easier. The challenge in this lab is figuring out how to take these 2 bits and these 2 bits and manipulate them in some way so that they look like 2 8-bit numbers that we can just add with the add instruction. In other words, what we'd like to do is take that number that we read in, this 8-bit port B number, and change it to look like this. We would like to create some general file register inside. Maybe I'll just call it number 1. And have it look like this. And we'd like to create another number, number 2, and have it look like this. Because if we can take these 2 bits and copy them here and make all of these bits 0, and then take these 2 bits and copy them here and make all of these bits 0, now we can ask the PIC processor to just add number 1 and number 2, and it'll add them together. And it will give us something like this. We know those upper 5 bits will be zeros, but those lower 3 bits will be the sum. And then we want to somehow turn that into something that looks like this. So here's what's happening. We read port B, we know how to do that. We set up ADCOM, we set up TRISA, and we just read the register called port B. We want to copy these over to here and force all of these to 0. And then we want to somehow copy these over to here and force all of these to 0. And then we want to do an addition. So this is the PIC add instruction. Gives us this, and then we want to somehow move these things over and force all of those to 0. And then we want to send this to port B. And what you're going to do is on on port B, those 8 pins, RB0 through 7, you're going to hook up 4 switches, RB0, 1, 2, and 3, and you're going to hook up 3 LEDs, RB5, 6, and 7. And if you do this, whatever value you have on those switches will get added together, and those LEDs will light up and show you what the sum is. And it's really satisfying when you get that to work. And on a whiteboard, it's not that hard, right? Take these things, copy them down, put zeros here, take these things, move them over, put zeros, add them together, that's 2 instructions. Take the sum, move them over here, put zeros, copy that to port B. Go back to the top, do it again. The real part that gets confusing here is this business of 2 things. One, moving these things over. We need these B1 and B0 to move over from these positions to here. We need our sum to move from these positions over to here. The other part is filling in these zeros. Whatever values we got on here, we want zeros in these upper 6 locations and then A1, A0 here. And we could say bit clear, bit clear, bit clear, bit clear, bit clear, but that's kind of a lot of coding and you don't want to do that. So let me talk about how we do the shifting and how we do clearing of bits in general. And this again is general purpose stuff that will come up again and again, regardless of what processor you're using. So this first business has to do with what's called rotates, or sometimes shifts. So back to table 20-1. And about halfway down that first page, you'll see 4 instructions. This is rotate left with carry file register, rotate left with no carry file register, rotate right, rotate right. All right, for today, ignore these. Let's just look at the NC ones. Rotate left, no carry file, and rotate right, no carry file. And what this does is it takes all the bits in a file register and it shoves them over one position, either left or right. So let's say, file register 80 contains this, 1001, 0100. If I say rotate right, no carry file register, hex 80, it shifts everything over to the right one position. So this will become 1, 0, 0, 1, 0, 1, 0, with an extra 0 in the front. Basically, everything moves over one spot. And this last one wraps around, comes back in the beginning. And if I do another rotate right, no carry F on the same location, everything will move down another position. And if I do it a total of 8 times, I'm back to the original value I had in there. And if you rotate left, it just goes the other direction. So if I were to take the value of part B and copy it into a file register, and then say rotate right, no carry, rotate right, no carry, the value I read would look like this. All right, well, let me not skip steps. So if I do one rotate right, it looks like that. And if I do another rotate right, then it looks like this. And now, these two things are in the position that I'm going to want them to be in to make my second number. So now if I could force all of these to be 0, I've got my num2. And this, my sum, if I rotate that right once, what does it look like?
Zero, 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 zero. That's good.
That's two as well.
And if I rotate again,
So you have those 3 times.
right, and then if I do it a third time. And now it looks exactly like what I want to write out to port B. So rotates are your friend, right? There's no way around them. No convenient way around them. All right, the other question is zeroing out a bunch of bits. Suppose I read from port B, copy port B into some file register, let me call it num1. So num1 looks like this. And what I want it to look like is this. Well, I mentioned that we can do logical operations. We can do a bitwise AND, an OR, an XOR, or a complement. And if you logically AND two file registers, it ANDs them bit by bit. So suppose I AND this register with a value like this. This bit, whether it's a 1 or a 0, if I AND it with a 0, it's going to become a 0. This bit, whatever it is, I'm ANDing with a 0, it's going to become a 0. These 6 bits, I'm ANDing them with zeros, these will all be zeros. Well, what happens if you AND something with a 1? What do you get?
Zero.
What if you get a 0 and you AND it with a 1?
Still get the 0.
What if you get a 1 and you AND it with a 1?
1.
So when you AND something with a 1, you get that something back. It doesn't change it. So A1, whether it's a 1 or a 0, when I AND it with a 1, it's still going to be A1. And this is still going to be A0. So if I take the value I read from port B and I AND it with this number, which is 3, I'll end up with this. And that's exactly what I want for my num1. Now I can read port B, I can rotate it twice, make it look like this, AND it with 3, that gives me my num2. Tell the pick to add those together, take the sum, rotate it to the right 3 times, write that to port B, you're done. So this is called a bitmask. And bitmasks pop up all over in assembly language programming. And the basic idea is if you AND something with a 0, it becomes a 0. If you AND with a 1, it doesn't change. What about if you OR with a 0? It stays the same. And if you OR with a 1, it goes to a 1. So if we want to set certain bits to 1 and leave other bits unchanged, we'll do an OR with a bitmask. If we want to set certain bits to 0 and leave other bits unchanged, we do an AND with a bitmask. And what about an XOR? What if you XOR with 0? This one's tricky. It's a 0, 0, 0. What's 1 XOR with 0?
1.
1. So if you XOR with a 0, it doesn't change. What if you XOR with a 1?
0 XOR with a 1.
Mm-hmm.
Still 1.
And what about 1 XOR with a 1?
0.
So if you XOR with a 1, you toggle. So if you want to flip certain bits and leave other bits unchanged, you do an XOR, you put a 1 where you want to flip the bit, and you put a 0 where you want it to be the same. So bitmasks are really powerful. They're a way to do what we do with bit clear, bit set, bit toggle, but to do it with a large number of bits. And the more proficient you are with bitmasks, the quicker you'll be with doing anything related to I/O on pretty much any processor. So bitmasks are pretty key, and they're fun to play with. All right, so we need some nuts and bolts because we don't want to outsource portions of this code to other people to write for us. So let's go through some mechanics of doing certain things in the assembly language. And all this stuff you can mess with in the simulator, right? You don't have to get a PIC chip and program it and deal with all that. You can do all this in simulation. And most of the lab you're going to do in simulation. Once your program's working, hooking up the PIC chip, like I say, it's a dip switch, it's 4 inputs, it's 3 LEDs. It's a pretty simple circuit compared to what you've done in other classes. It's the software that's the real effort here, and you can simulate that all day. So let's look at software mechanics. So we know about, let's see, let me give you a detail first. Put that in the beginning of your program. Double quotes. Number sign include, quote, P18F1220.inc, quote. Let me show you what that does. That gives you a file that basically gets pulled into the beginning of your program. It's as if you typed all of this, which is about 1,000 lines of assembly code. It's as if you typed all of that in the beginning of your program. So it's got some comments, it's got a no list thing, so this doesn't show up in your disassembly listing. But most of what you find in this file are these EQU statements. For example, port A, EQU, hex 0F80. And once you've included this file, you can use PORTA uppercase, and every time it sees that, it'll replace it with hex F80, which is the address of that special function register. Here's TRISA, that gets replaced with F92. And if you look on the back of your cheat sheet at those special function registers, these should correspond to these labels. So we don't need to know that port A is F80 and port B is F81. If you include this file, you can just use port A, port B, tris A, tris B, addcon1, and so on, and it'll replace it with those. The nice thing about this is, one, you don't have to remember these magic numbers, but two, if you switch to a different type of processor, these will all change. Port A won't always be F80. It might be some totally different location. And rather than going through and changing all your magic numbers, if you say port A, but you include a different file for the new type of chip that you're on, these will all be set up correctly. You reassemble and you're good to go. So this file defines all of these different special function registers, and it defines some abbreviations like RA0 and AN0, and it just kind of goes on and on and on. All that good stuff. All right, so include that in the beginning. And then we can talk about SFRs, including, do you remember this one? So that's the working register. And you're going to need to heavily use the working register anytime you want to do pretty much anything. Because we can put this comma 0 or comma 1 after our instructions to force it to write a result to either the file register we're operating on or the working register. that's your reminder for it. So, comma 0. Result goes to your working register, comma 1. Your result goes to file register. And by the way, anyway, comma F and comma W should be set up in that include file. So you can say comma F or comma W, but everything in the book says comma 0 or comma 1, so you may as well learn it like that for setting your destination. All right, so we can increment a file register, INCF. Let me, I don't know, variable 1 equals x80. So I could say increment file register, variable 1. And that just reads the contents of location 80, adds 1 to it, writes it back. If I do comma 0, it reads the contents of that file register, adds 1, and writes the result to the W register. And it does not change the file register. So this actually says var1 plus 1 gets loaded into the working register. And if I say increment file var1 comma 1, this says var1 plus 1 gets loaded back into var1. And I'm pretty sure this is the default. So if you don't specify comma 0 or comma 1, I'm 99% sure it goes to the file register. Because that's usually what we're doing. But if you want to go to the W register, put in a comma 0. All right, what if we want to add 2 to variable 1 and write the result back? How do we do that? This will add 1 to it. What if we want to add 2?
Put a 2 before the F?
That would be nice, but nope, that doesn't work. What's the lazy way to add 2?
Do it twice.
Do it twice. Nothing wrong with that. So now variable 1's been incremented twice. It's got its old value plus 2. And that's actually as efficient as the other way to do it. But what if you want to add 17 to variable 1? You probably don't want to do 17 increments, right? And we do have an add instruction, but let's take a look at it. So we have an add WF, add W register and F. And that's our only choice. We can't just take 2 file registers and add them together. There's no instruction for that. Why? Because there's not enough space in most of our instructions to store 2 file registers. These 16-bit instructions, we use 8 bits to specify 1 file register. That's it. We don't have another 8 bits to spare. So things like add and subtract and compare and all of this, we've got to work with the W register. Well, so I want to add 17 to variable 1. If I had a way to get 17 into the W register, I could say add WF. And that would add the W register, which has 17, and the file register, which is var1. And then I could say put the result back into var1. So load 17 into WREG, and then add WF var1 comma 1. And this will say var1 plus 17 goes into var1. So having that working register available makes life really easy, because most of these instructions have variants that we can use the W register to work with. But how do we get 17 into the working register? We could clear it and increment it 17 times, but that can't be the best way. So there's a special set of instructions called literal instructions. And they're on this third page of our favorite table. And it's these instructions here. And the one we're going to find most useful is this move literal into W. So move literal into W lets us write something like this. Now, every instruction we've written so far, this was a file register number. If we say increment file register 17, it reads the value of register 17, adds 1 to it. A literal means this is not supposed to be interpreted. It's supposed to be taken literally. It's actually the number 17 that we're loading into the working register. So this instruction says 17 goes into WREG. Not the contents of file register 17, just the plain old number 17. And then if I say add WF var1, since W has 17, this takes 17, adds it to var1, and the comma 1 says write it back into var1. So there's how I add 17, or any number, to my variable. So literals are key. It's a way to take a constant value from 0 to 255 and load it into the W register. And there's a number of literals. For example, we can add a literal value to the W register with one instruction. So if the W register has some value that I want to add 5 to, all I have to do is say add literal W5. It'll take the number 5, add it to W, put it back in W. And when you code these, there's no destination bit, there's no file register involved, it's just working on the W register. So these 8 bits, these encode the actual literal value. So if I'm doing move LW17, the outcode would be 0000, 1110, and then the 8 bits that correspond to 17, which could be hexadecimal, I haven't specified. So move literal into W will be really key. The other big thing we'll do is move data between file registers and the W register. And there's 2 ways to do this. So one is move WF. This moves the W register into a file register. So if I have a value in W and I want to move it somewhere, either into a general file register or to port B or to TRISA or something else, the instruction is move WF followed by the file register. And there's no destination bit associated with this, so you don't put a comma 0 or comma 1 after that. So if I want to set var1 equal to 42, what can I do? Move literal into W, 42, that puts the number 42 into the W register, and then move W register into file register, var1. This copies the W register to var1, and since the W register is 42, var1 is now equal to 42. So you should think of the W register, the working register, as a scratch pad. It's a temporary storage that you're going to use as a go-between from one place to another, because some instructions only work with the W register. We can only load literals into W. We can only add a file register to W. So it's a temporary scratch pad usually. So 2 instructions, we can take 42, put it into W, load it into var1.
So does that mean you have to reset it every time you want to start moving to different variables?
If you wanted to load a bunch of different values into different variables, you'd have to do these two steps again and again. Now, if I wanted to load a bunch of variables to all be equal to 42, I can load 42 into W once, and then I can just do a bunch of move WFs.
Okay.
And that would be the same. So if I followed this by move WF, that would load 42 into var 2. So this copies the W register into a variable. Suppose I want to do the opposite. Copy var1 into the W register. How the heck am I going to do that? So I've got a value in my file register. I want to copy that into the W register. And it's a quirky operation. And I had to look it up when I was first doing this. There's an instruction called move F, which says move a file register. But remember, we don't get to specify two different file registers in most cases. Increment, decrement, clear. Take the result and they put it in one of two places, back in the file register or into the W register. So if I say something like this, with a destination bit of 1, which means right to the file register, this does var1 gets copied to var1. Which it's not clear we have a reason for doing. So we'll make that a comment. But if I do this, move F var1 comma 0, that says read from var1 and write into the W register. So this does what we want. Copies the general file register into the working register. So if I want to read port B and load that into the working register, move F port B comma 0 will do it. If I want to read port B and load it into variable 1, I've got a few options. So let's say copy port B to variable 1. Always think of the working register, it's your scratch pad. Well, if I don't know how to copy port B to variable 1, I do know how to copy from a file register into the working register. So I can say move file port B, comma 0. So now our WREG is equal to port B, and then I can say move WF var1, and now var1 equals whatever's in the working register, which was port B. So those two instructions will read from port B and copy the value into variable 1. But it turns out we also have a special instruction that we can use that's equivalent, and this is another one of these two-word instructions. It's called move FF. And move FF is the one instruction that will take two file registers. So we can actually say move FF and name our source file register and name our destination file register. And this will do the same as this. And it takes just as long and it takes just as many bits of instruction. But for some people this feels a little cleaner. And if you look in table 20-1 at the coding of move FF, first one is the first file register, and the second one is the second file register. All right, let's see, what else do I need to tell you? Positively, definitely. Let me talk a little about branches. And I'm not going to talk about how to code branches into assembly language, into machine code today. There's some questions on it, but we can go over those on Thursday. You can read them and take a shot at them. But let me talk about branches in general. So here's the beginning of our program. Here's some stuff we want to do. And at some point I can have a label. Starts in column 1, ends with a colon. It can be pretty much any reasonable label that you want. So loop or start or repeat or whatever, I'll just call it label. And somewhere in my instructions, I can say branch label, and it's like a go-to. It will say, okay, instead of executing this instruction next, go back and execute the first